Okay, so we're going to switch gears a little bit into the solar system from these black holes that are much further away, and talk about our local debris disk, which is really what the Kuiper belt is. So just to give you a view of where I'm going, we're going to talk about the very simplified picture of how planetesimal-driven planet migration happened in our solar system, what we know about this process and why we might care about this process, and then how we're going to actually learn more about this process by studying the Kuiper belt through the Outer Solar System's Origins Survey, or OSSOS. So the big picture is that in the early solar system, Jupiter, Saturn, Uranus, and Neptune formed closer to the Sun than where they are today. They were in a more compact configuration. And then we have this massive planetesimal disk exterior to the giant planets. And what happens if you set down planets with this massive disk outside is this. They're going to gravitationally interact. The objects are going to scatter off of the planets, and the planets are going to migrate around in response to the gravitational interactions with these planetesimals. So you've seen that we started with this more compact configuration, and then the planets have spread out in reaction to gravitationally interacting with the disk. And so this is just someone else's simulation and nice video, because I'm terrible at making videos. But the idea here is we're done with the gas phase. So this is you formed the planets, the gas is gone, and really we're just interacting with these planetesimals. So at some later time, you've got the planets that have spread out. You no longer have much stuff left over in here, but we're left with a debris disk that's much reduced in mass compared to the beginning, and that's what we see in the current Kuiper belt, which is basically all the small objects that are outside of Neptune's current orbit. And this is an observational picture. We've got semi-major axis on the bottom axis, and then eccentricity and inclination. And some important features to note here are that we've got this condensed version of fairly unexcited orbits. They're fairly circular, fairly low inclination compared to the planetary plane. But you've got this nice kind of scattered out disk. So this is perihelion distances of 30 and 40 AU. So anything with a perihelion distance between 30 and 40 is at least weakly interacting with Neptune, which is at 30 AU. So these are things that are actively kind of random walking in semi-major axis in response to these gravitational interactions with Neptune. And the blue dot there is Pluto, just because everybody knows about Pluto, so it's a nice reference point. So this is just a zoomed-in view that also shows that we have some other features here, which are resonances with Neptune that I'm going to come back to later. But you'll see that this fan shape of objects that have scattered off of Neptune is kind of reminiscent to this similar shape in that simulation. So this was not a simulation of our solar system, but it's kind of generic that after you've gravitationally interacted with the disk, you're going to end up with this population of scattering objects that's left out there. So this is just the basic structure of the Kuiper belt is fairly understandable as a result of having interacted with the planetesimal disk. But if we zoom in on just the inner part of the Kuiper belt, which we kind of call the classical Kuiper belt, we can see some more interesting features. Like I said, we've got this kind of cold, low inclination, low eccentricity, dense population of objects. But then we've got this excited population called the hot classical Kuiper belt, which is higher eccentricity, higher inclination, things that are still not too far outside of Neptune's orbit. And we can again see a little more of this resonant feature. And if we zoom in, there's two resonant features. Yeah?
Just to clarify, these are observations or simulations?
These are observations. So, and I should also note, this is totally biased. So this is flux limited, depending on where we point it. So this is not a true picture of the Kuiper belt, but we can still see a lot of these features by just looking at what we see. So I'll get into the more what these biases do to our observations. But here are the two mean motion resonances we can kind of see in this picture. There are a lot of other resonances in here, but the 3-to-2 mean motion resonance with Neptune is very obvious. There's a lot of objects here. We see that very well when we look because they have high eccentricity, so they come in close to the sun. They're easier to see. Little less obvious here is the 2-to-1 resonance. It's further away, so we don't have as many observed objects in there, but you can start to see the resonance structure even before we worry about observational biases. And And the resonances are important because that was one of our first clues to how the planets have migrated out. Because one of the early ideas was, why is Pluto in this mean motion resonance with Neptune? How did it end up there? And the idea is that if Neptune is moving out in response to the interactions with the planetesimal disk, its resonance locations will also move out as Neptune moves out. And you can capture objects into the resonances as they kind of migrate outward. So this is a very simplified picture where we've just got nice smooth migration. The planets are well-behaved, low eccentricities, and the resonances smoothly migrate out in time with the planets. And this is most likely not what happened, but it's a nice picture to keep in mind. So that was, a very simplified view of how we might naively interpret the Kuiper belt based on how it interacted with the planet system. But there's a lot of details missing here. One is, does this make sense in context of what we now know about exoplanet systems? We also want to know, when did this process occur? How soon after the gas disk was gone did this occur? And exactly what happened? That nice, slow, well-behaved marching outward thing that I just showed on the last slide, that's probably not what happened. We want to know actually what happened. What are the details? So in terms of our understanding with other planetary systems, one of the first things to ask is this starting configuration common? Is it common to have a kind of compact configuration of giant planets with this planetesimal disk outside? And it turns out this does look fairly common. You can observe these disks indirectly in exoplanet systems. You're never going to see the objects themselves. They're tiny. But when they're in a giant population like this, there are collisions, and those collisions produce dust. And you can see the dust in infrared observations. So you can infer the presence of a debris disk like this in the infrared. And this is just an example. And it turns out that when you survey solar-type stars, it looks like debris disks starting at 15-ish AU and extending out to a few hundred AU are pretty common. So that's nice. Is a common starting point probably for planetary systems. So it shouldn't be unusual to go from a compact configuration like this, let things interact, and then go out like this. So I said I was going to discuss why we care about this process other than just, it's always nice to know what happened, but what are some other effects of this, and how it affects the inner solar system is particularly of interest because we're in the inner solar system, we're on Earth, and we might like to know what would happen to Earth when the giant planets are undergoing this huge rearrangement. And one of the things that could happen to Earth and the other terrestrial planets when this rearrangement happens is orbital instability. So this is from a simulation where just one particular configuration of the outer planets, you let it go, you let the outer planets rearrange themselves, and a bad thing happens in the inner solar system in this particular simulation. You have secular resonances that affect the orbits of the terrestrial planets. And these secular resonances in this particular simulation cause Venus's eccentricity to grow too large, and then you have Venus and Earth on planet-crossing orbits. That's bad. That can't have happened because Venus and the Earth are relatively stable today, and they did not hit each other in the past. So this is one of the effects on the inner solar system. So you've got these secular resonances that affect the orbital eccentricities. So this is a constraint on the process that we can use to say, well, this didn't happen, so we need to let the terrestrial planets be stable when the outer solar system is rearranging itself. Another thing that can happen when you let the outer solar system rearrange is that the asteroid belt, which is sitting just interior to Jupiter's orbit, is full of all sorts of nice projectiles. And when the outer planets move, Jupiter's resonances and Saturn's resonances move around in the asteroid belt, just like Neptune's resonances move. And these can destabilize asteroid orbits. And the asteroids leave the asteroid belt. And then when they leave the asteroid belt, wham, they start hitting the terrestrial planets. You get craters. So this is another reason we want to know when this happened and how badly it destabilized the terrestrial planet region. Because if you look at the impact records in the inner solar system, you notice an interesting thing, which is a spike. This is a cartoon of the impact frequency in the inner solar system likely on the moon as a function of time. And we're pretty sure that the impact rate went up at about 3.9 billion years ago, compared to, accretion of the planets is happening 4.5 billion years ago. And we know that the accretionary impact flux dropped off, but then something caused a spike in the impact flux at 3.9 billion years ago. And this is of astrobiological significance because Earth probably life on Earth probably arose shortly after this impact flux. So we kind of want to know what happened to cause this, and maybe it's tied to this idea of the giant planets rearranging themselves. So they're all just kind of motivating factors for why we care about what happened in the outer solar system.
I don't know if this is your area of expertise, but could there have been life before the heavy bombardment that the evidence for it was covered up? Or do we know?
It's not my area of expertise, but I think that's entirely reasonable. I don't know how much evidence would have been able to survive the bombardment, so. Yeah, I mean, maybe that's where we got our oceans. Maybe, we know that the water had to be delivered to the Earth somehow. So yeah, there's lots of questions about the Earth's past that might be linked to figuring out what happened in the outer solar system, because the outer solar system controls what happens in the inner solar system. So that's just all motivating material for why we want to know whether this sort of nice smooth process happened, or maybe it was a much more violent process where we have the giant planets. In this case, it's Jupiter, Saturn, Neptune, and then Uranus in a compact configuration, and they kind of hang out, and then there's a resonance crossing that excites all of the giant planet orbits, and you get giant planets scattering off of each other, which is entirely different than that nice, smooth process we had. And
why does Uranus have two curves in this plot? Why is the Uranus curve split into two?
Oh, that was showing perihelion and aphelion distance, so this is just showing that the eccentricity grew. And of course, there's a nice video of this, except if I make this full screen, I don't know how to make a video show up on here.
Drag the window off the side of the screen so it appears like that.
Oh, except now I can't.
It's running now.
All right, I can't get back to that. Anyway, there's a video that shows the outer solar system exploding in response to the planetesimal disk. It's just an animation of this.
I would love to see it, but somebody will plot.
I don't know how to work, since it's not mirroring the display. It's in Safari. Okay, yeah. So this replay. There we go. That's good enough. Okay, so we've got the proto-Kuiper belt here, the more compact configuration, and time is up on the top there, and this is the Nice model of the outer solar system. So you can see it's hanging out for a few 100 million years. So this is a potential way. You have this quasi-stable state for a few 100 million years, and if you wait for it, Jupiter and Saturn are very slowly moving in response to interactions from the planetesimal belt, and they're going to cross their mutual resonance, and the whole thing's going to blow up real soon. And boom, you have a mutual excitation of the giant planets that completely reconfigures the outer solar system, like nearly instantaneously. It happens very fast as opposed to this kind of slower, smoother migration. And then the remnants of the disk help calm the outer planets' orbits down, shrink their eccentricities to what we see today, and leave us with the outer solar system as we see today. So, as you might imagine, these scenarios should leave a signature in the Kuiper belt, because the Kuiper belt is what's left over from this process. It's the bodies that are still around from that original debris disk that caused the rearrangement of the outer solar system. So that's our best shot at figuring out what actually happened there. So to do this, we want to know what are the features of the Kuiper belt that are just, mostly determined by this process of the giant planets rearranging themselves. Did different parts of the Kuiper belt maybe come from different parts of that initial debris disk? So maybe specific parts of the Kuiper belt formed closer to the sun than others, so they'll manifest some physical differences that can point to their origins. And then my particular area of research is how exactly did we fill these resonances with Neptune? Because how we filled them will give us a clue as to how the planet migration process went down. So, some things that we think we understand are that, this debris disk before the planets rearranged themselves was roughly 100 times more massive than it is today. So planet migration is probably the best way to explain how we got rid of most of the mass of the Kuiper belt. We needed to explain, how did we get these really large inclinations and fairly large eccentricities in the outer solar system? You would not expect a debris disk to have an inclination function that has a peak around 20 degrees. So remember, this is just observed. This has biases. A lot of the surveys of the outer solar system are done close to the planetary plane. So it's a lot easier to see these guys down here than to see the stuff that spends most of its time highly inclined from the ecliptic. So when you actually take out the biases here, there's a huge population of highly inclined objects. So we've got to explain how we got those inclinations. And also, we see some differences in the physical properties that I hinted at, between these low inclination, low eccentricity objects and these more excited objects. They appear to have a different size distribution. They have different color distributions. They have different fractions of binary versus single objects. And these all point to different formation locations in that original planetesimal disk. And most importantly, planet migration is how we're going to explain the large number of resonant Kuiper belt objects. So this is just a cartoon of all of the mean motion resonances that are observationally occupied between Neptune's orbit at 30 AU and about out to 50 AU. And these are the numbers of objects in each of these resonances. That's a lot of objects in resonance. And without some capture mechanism, you would not expect to see that many objects in resonance with Neptune, especially in some of these really high-order mean motion resonances.
So Morby used to argue these were just capture after the fact, right?
Yeah.
Stochastically. Is that definitely not true?
Well, I mean, it just, you wouldn't expect to see quite this many objects in the resonances. Now, depending on exactly what's going on with the resonances during migration, this idea of picking them up as the resonances slowly sweep out, that's not necessarily going to have to be the case. But another case is, what if Neptune's eccentricity is higher at some point in the past, like in a Nice model scenario where you've had Neptune scattering, it has a high eccentricity for a short phase, so that all these resonances, which are eccentricity-type resonances, are going to be effectively wider because Neptune has a larger eccentricity. So you can capture objects that way because of the higher eccentricity.
Are there any resonances which are unoccupied?
Unoccupied?
Yeah.
Well, yeah. So the tricky thing with...
I'm just wondering, how significant is it to have one object with a resonance? Like, is it like, oh, there's something special here? Or?
One object is probably not significant because that's just small number statistics, and the exact numbers, so these resonance identifications depend on how well you fit the orbit. So some of them may or may not be in resonance. But, having 100 plus is definitely significant. Out here having 20 or 30 is significant, especially because they get harder and harder to see the farther out they are, because these are small objects. So the further away they are, the more your flux limit in the survey affects how many objects you can see. It's really tricky to find out, intrinsically, what do these numbers translate into, in terms of how big the populations are in the resonances, is one of our goals with OSSOS. So I'm going to come back to that. Because it turns out to be very tricky to figure out what the biases are in determining the number of objects. But it's a very complex set of resonances that are occupied. And there are lots of unoccupied resonances because there are an infinite number of possible resonances. And it's a whole other area of research into what resonances are important that I won't go into today. But yeah, it's a complex field of study. And as I said, we need better observations to be able to tell what does what we see actually mean in terms of the intrinsic population. And that's where OSSOS is going to come in. So this is the Outer Solar System's Origin Survey. It's a long list of collaborators. This is using the Canada, France, Hawaii telescope. and they're doing a very large survey, and we should get something like 1,000 new Kuiper belt objects. But the really important thing is that it's being done in a very systematic way that allows us to construct a survey simulator. So we have these 1,000 detected objects. I can create a model of what I think the Kuiper belt looks like, feed it through a survey simulator, and compare those simulated observations to the actual detections. And I can quantitatively say how good my model of the Kuiper belt is, which is not something we've really been able to do yet, because those scatter plots of nice dots I showed you are from a lot of different surveys which had different limitations, different biases, and it's really hard to say anything quantitatively about how well your model fits those observations, which is why one big, nice, really well-characterized survey is important for helping us figure out how well our models are doing. So I'm going to come back to why particularly this is important for measuring the resonant Kuiper belt populations. So when an object is in resonance with Neptune, that means that we're conserving this resonance angle that has to do with the longitudes of the Kuiper belt object in Neptune and its argument of perihelion. This is the dominant form for, like, say, the 3 to 2 Q to P mean motion resonance. That's the dominant resonant angle, involves the longitude of eccentricity of the Kuiper belt object. Since the Kuiper belt object's eccentricity tends to be the highest of the, between Neptune and the Kuiper belt object will have higher eccentricity. But what this resonance angle means is that if you're looking down on the system, and you're in a rotating reference frame, so Neptune's position is fixed. We've got the Sun and Neptune, and this is a evenly spaced time sample. So you run a simulation of one object in the 3 to 2 mean motion resonance with Neptune, and you just evenly sample its position and plot it here. You can see that being in resonance controls where this object comes to perihelion relative to Neptune's position. So perfect resonance would have the object coming to perihelion here and here over repeated orbits. And then because this angle is not perfectly conserved, it's actually librating. You get this spread in where the object comes to perihelion. But say that it's a small object, we're only sensitive and able to see it when it's at perihelion. That means that we can only see it on the inner edge of where these dots are forming. So you can kind of start to see that, we're somewhere in this plot on Earth, and we're pointing our telescopes at the sky. So if we point our telescopes along this line of sight, we're never going to see this object because it's far too faint when it's furthest from the sun. But if we point our telescope along this line of sight, we'll have a much easier time seeing the object. So you can imagine that exactly where you've pointed in the sky relative to where Neptune is will determine how likely you are to discover objects in the 3 to 2 resonance. And every resonance is going to have a different pattern of librations and a different location of where it comes to perihelion relative to Neptune. So you can perhaps start to see why this is a really complicated observational task to say, I did a survey and I did or did not see objects in this particular resonance. What does that mean for the intrinsic population of that resonance? And the answer is going to depend on where you pointed your telescope. So it becomes a very complicated problem, which is why a well-characterized survey is so important. So what I am trying to do is build up models of what will that plot look like for the resonant objects in the case, the one end member case where we have this smooth planet migration. That's an oversimplification of one type of planet migration. And how will that capture objects into resonance? So this is just a simulation of a test particle being captured into resonance as the resonance is migrating. So this is its semi-major axis of Neptune and semi-major axis of the test particle. And Neptune is migrating outward. Its resonance is migrating outward. And about here in the simulation, this object is captured into resonance and then gets dragged outward as the resonance goes outward. And this is that resonance angle going from circulating, meaning we're not in the resonance, to a well-defined libration pattern. So that's how you capture objects in resonance in this smooth migration state. But what about in a situation that's more like this, where you're capturing objects because the resonances are wider, because Neptune has a high eccentricity, and then you keep some fraction of the objects in resonance because the eccentricity gets damped. So this is a much messier plot of capture in that case, where we've got, again, a Kuiper belt object test particle in orange. It's kind of scattering around. At some point, it does get trapped in the resonance. The resonance angle does something messy, but it is librating. But the point is you can run statistical simulations of these two kind of opposite cases of planet migration. And you can come up with what would this resonance look like in either case. And this is that libration amplitude. So just for the 3-2 resonance, for example. And in the situation where you're capturing them because Neptune had a higher eccentricity, this is kind of the distribution of libration amplitudes you get versus a smooth migration case. And those look marginally different. You can get different distributions there. This is our observed bias distribution just for reference. It doesn't look like either case, and it's biased, so we don't have an answer as to what the libration distribution actually looks like yet.
So my question about the 3-2 has two resonances, and you're saying there are no objects in the other resonance with one involves longitude of Neptune?
I don't think there's any current ones librating in that resonance argument. There are certainly no objects librating in that resonance that are not also librating in the KBO's eccentricity argument. But that could also be, the orbit fits are not perfect, so I don't think there's any librating in that argument. Anyway, so we can get these libration amplitude distributions. We can compare them statistically and say, how many observations would we need to be able to distinguish these two end-member cases? Just using a KS test to have 95% confidence level of telling those two distributions I showed you apart. It's 75 or so observations that you need, 150 observations to tell them apart at the 99% confidence level. And right now we've got about 100 observations of Plutinos, but they're very biased, so you can't really use them to tell them apart. But with OSSOS, we should get about 200 Plutinos, and we will know the biases, so we can actually calculate what the intrinsic distribution is. So we should be about here when we're done with OSSOS in a couple years. So that's promising. We should be able to rule out either one of those end-member cases and say, my guess is we'll rule out smooth migration. We may or may not. There's a lot of different variations when you're scattering Neptune and allowing that to happen. So I'm not sure it will definitively answer the question of what happened, but we should be able to rule things out. And then there's another sub-resonance within some of the resonances called the Kozai resonance. Basically, Pluto is in this resonance, and what it means is that you're in this 3-2 mean motion resonance with Neptune, which controls where you come to perihelion relative to Neptune. But then on top of this, there's a secondary resonance that says when you come to perihelion, you're going to be at your maximum excursion above the ecliptic plane. So you're always going to be, basically at the peak of your inclination when you come to perihelion. And the fraction of objects in the secondary resonance will also differ between the two scenarios. It's in fact a slightly bigger difference than between the libration amplitude distributions. So 25% in this kind of smooth case, and that's a hard lower limit. It's more than that in a lot of cases, depending on your initial conditions. Something like 10% in a Nice model type scenario. Our best estimate right now is that it's less than 33%, which conveniently does not rule out either of these scenarios yet. But that's another thing we should be able to determine from OSSOS. So we should be working hard at producing these models that make predictable, good predictions as to what we should see when we actually understand the intrinsic distributions. And that'll allow us to start ruling out certain situations for what happened when we reshuffled the outer solar system. And that's just my small part of the OSSOS collaboration. There are a lot of other studies being done. There are follow-up studies of physical properties. We should be able to answer a lot of questions about the Kuiper belt at the end of OSSOS. So I've just told you about my particular subset of that collaboration. So it should be exciting. We'll know a lot more about the outer solar system in a few years. Thank you.
Plenty of time for questions. I'm assuming you Seeing of different resonances?
Yeah, everywhere would be fantastic, but there's not enough time. So there are all-sky surveys at brighter limiting magnitudes. I don't think they've been done with MegaCam. But so OSSOS is going to something like 24 and a half in R band. So the all-sky surveys, I think, have gone to like 23. That's as deep as you can really go and try to cover enough sky. So OSSOS, the strategy is that they have targeted blocks. So we have some idea of what the distribution of Kuiper belt objects looks like, within the resonances from all the surveys that have already been done. So they used those models to target the blocks. And they've made sure that the blocks will optimize discoveries of objects in the 3 to 2 mean motion resonance and as many other resonances as possible. So we should get large numbers in the 3 to 2 because that has specifically been targeted. They have put the blocks where they're going to catch most of the 3 to 2 objects coming to perihelion. And there are blocks that are on ecliptic and blocks that are off ecliptic. But it's far from all sky. So we are going to miss some of the resonances. But the real advantage to the survey is that the biases are completely known. And there is a survey simulator. And the survey simulator, says exactly what was the limiting magnitude on this night of observation, so it accounts for all the parameters of the survey. So it's, that's the best way. So there are kind of two approaches to debiasing your observations. You can say after the fact, you can kind of try to divide out the biases and do it that way, or you can feed a model into a survey simulator and then compare simulated detections with actual detections. So we're taking the survey simulator approach because that's the more complete approach. But,
Each block is, how big is the size actually? Is that
20 square degree. I think it's 20 square degree blocks.
Okay.
So they're not small, but there's a lot of sky, so it's going to miss a lot of sky. But they're targeted for really precise astrometry, so that every discovery in the block will yield a very good orbit fit, which is another thing that's important in the resonances. So if you have really high astrometric precision, then you can fit an orbit to these objects after only about 6 months of observations. So in the past, it's taken multiple years to get really good orbit fits. But they're applying some newfangled plate-fitting astrometry thing that I don't entirely understand that is allowing them to measure the positions of these objects to much higher precision than past surveys. So I've seen the orbit fits after only 6 months of observations in some of these objects, and they're good enough to say that is resonant or it is not, which in the past has taken multiple years to determine. So
You're seeing like 1% of an arc, though.
yeah. I mean, the orbital periods are hundreds of years.
Exactly.
So you're seeing, and so I think the idea is to get 6 months and up to about 18 months of recovery. So I think each block is going to get observed, have at least a year of arc in the end. But yeah.
So you said that you're hoping to discover around 1,000 new Kuiper belt objects. How significant is that number compared to, the population of presumably less massive, less luminous objects? I mean, when you compare your simulations, I can understand, you can put 4 planets in, that sounds fine. And you
Yeah.
can put in short order thousands of particles, but is there concern that there's, a low mass end of these objects that have some, play some role in how the system's developed? And is that an issue when you come to compare your simulations to your, resonance numbers?
Yeah, that's always going to be an issue. The Kuiper belt is not that massive today, so the effect of the total mass of the belt on my orbital simulations is not going to be huge today. But in the past, it was something, a few Earth masses of material, so that becomes important, and I'm neglecting that. But we do have a slight handle on how many objects there are that are going to be fainter than what we can see with OSSOS. So there have been what we call pencil beam surveys, where they look much deeper in a much smaller area of sky. So we have some sense of the size distribution at smaller sizes, but there's lots of stuff we're not seeing. We can only deal with what we can see in the survey, but
No, sure.
yeah. But that should be a minor factor. I mean, we're still failing to understand some pretty basic things about the Kuiper belt, so we can make a lot of progress before worrying too much about that sort of thing.
Right.
Yeah, good.
You mentioned biases. I was just wondering, do you sort of know what they do to the resonance distributions you observe?
Well, we know what they're going to do when we observe the resonance distributions in OSSOS. In other surveys, it's less evident because a lot of times when you report a survey in a paper, they will tell you the ecliptic latitude, which tells you how far off the ecliptic plane they were looking, but they don't necessarily tell you where they were looking relative to Neptune, so it becomes hard to gauge were they looking near the center libration or not. So yeah, like I said, for the 3 to 2, if you were to look, exactly opposite to Neptune, you're not going to see much because they will be at their farthest distance from the sun. So yeah, it matters a lot where you point.
So is that your main bias then, just the pointing?
For the resonances, yes, because they tend, the resonances are at a single semi-major axis. They have varying eccentricities, so there is a slight difference in what the flux limit does. But for the resonance, the primary bias is where were you relative to Neptune. For the rest of the belt, it's the flux limit, which is how far could you see. But for the resonances, it's direction.
So why do Neptune resonance trap countries most, whereas Jupiter resonance expel countries most?
I'm not sure we have a good explanation for that.
What was the question?
So why do Jupiter's resonances in the asteroid belt tend to evacuate things from the resonances, whereas Neptune's tend to be stable? So we collect objects in Neptune resonances, but we lose them in Jupiter resonances.
So Jupiter resonance is Jupiter's one more eccentric than Neptune and more massive.
Yeah.
So its resonances, there are resonances with different arguments associated, so it's different powers of the eccentricity of the planet versus the asteroid. And in the case of Jupiter, the resonances due to Jupiter's eccentricity are substantial. And so when you have
You have
mean motion
multiple.
resonance, you have multiple actual individual resonances. They tend to overlap in Jupiter, in the region around Jupiter. So that evacuates the resonances because those motions are chaotic. So you drive it to asteroid high eccentricity, and then it either hits Jupiter or it gets captured in a secular resonance, and then it hits the sun or the Earth or something. So it tends to clear out.
Yeah. You also have complicating factors like Saturn's Nu-6. It's not exactly Saturn, but there's a secular resonance at the edge of the asteroid belt that tends to help remove objects that have gotten to higher eccentricities and inclinations. So it's a little cleaner problem in the Kuiper belt. You can, for the most part, ignore the other planets. When you're looking at resonance dynamics, it really is dominated by a roughly circular Neptune. So it's a simplified picture. There are some issues, like Uranus's exact position does matter. There's some secular resonances, but once you get out, especially out, to the further resonances out past 50 AU, which I didn't even talk about, it's a really fairly simple dynamical problem. Like you can pretend it's just the sun and Neptune and the resonance, and you'll get a pretty good handle of what's going on.
When you do your simulations, do you just do Neptune or do you?
No, I include the giant planets. I don't do the terrestrial planets because I'm not using a time step short enough for that. But yeah, so there's some problems with that, especially when you're doing migration simulations. There are a lot of free parameters in exactly where you start the planets, exactly the speed that they go, so you have to make some simplifying assumptions. But that's why mostly when I talk about what we're going to do is rule out scenarios, it's going to be very hard to pin down the exact thing that happened, but we should be able to drastically reduce the number of free parameters there are when we're modeling that.
So you show us these histograms of vibration amplitudes in two scenarios,
Mm-hmm.
the smooth migration and the scattering.
Yeah.
How sensitive are these distributions to what exactly happens and when it happens?
They,
Could I, for example,
yeah.
get the histogram for the scattering to look completely different by having the planets scatter later or something like that?
Probably the time at which the scattering happens is not going to matter as much. So what's going to really change what these histograms look like, for this situation, what was Neptune's maximum eccentricity when it did the scattering event? I've made a simplifying assumption and assumed it's like 0.25 is the highest eccentricity it ever got. So that's going to affect this distribution.
Is that going to be a problem when we try to rule out this scenario?
No, so I did a whole suite of simulations here, and this kind of represents the two end member cases. So, it also depends on what initial conditions you assume for the Kuiper belt, which I guess that would change depending on the timing. But this is kind of the most similar they're going to look. Depending on what initial conditions you choose, you can make them look less similar. This one is harder to pin down because there's a lot more free parameters when you're talking planet-planet scattering and the eccentricities and what did Uranus do. This is a fairly well-behaved problem, which is why I think we're going to rule this out faster with the observations because there's a lot less wiggle room in that situation. So my guess is that in a couple years when we've got most of the OSSOS data in, we can rule out a lot of this. But this will be harder to pin down. But that'll still be a lot of information to rule out the smooth, well-behaved migration case.
Do we have an idea of the composition for these objects and how many of these objects do have an idea of the composition? And so, is there, do we see a correlation between, for example, the composition and the dynamical state? So,
yeah, so
there's this idea that the water content changes.
Yeah. So there are hints of some chemical composition differences, and that there is a sub-team on the OSSOS collaboration that's going to be dealing with that. So the tricky thing is these objects are so small that composition is measured by color. We can't get spectra or anything on most of these objects, so the color is standing in as a proxy for composition, but the colors are different depending on what dynamical class they're in. So some of the resonances look different than these really low eccentricity, low inclination objects. The scattered objects and the excited objects have different colors than the really low eccentricity. So there are hints that that is probably a compositional difference. But it's still a little hard. We don't know exactly what the colors mean in terms of compositions just because they're too small to see the spectra. And also you have to sort out things like surface weathering. You've got ices being irradiated and turned into organic material, which turns things red. But it seems pretty clear that there are differences in the sizes, there's differences in the binary fractions, and there's differences in the colors. So we are probably dealing with things that formed at different locations in the disk. So we're still sorting out exactly what that means in terms of where they came from and how that fits in with our dynamical models. That's going to be probably another big constraint. That's not my area, per se.
Last question?
Yeah, I think the smooth migration scenario is already ruled out because if you look at the inclination distribution, it's like that for the population.
Yeah.
Color distribution is like that for the host population. Binary fraction like that for the host population. Whereas in the smooth migration scenario, the resonant population would look rather like a cold population. And
Yeah.
so I think there is little doubt that it's not smooth.
Oh, that's,
migration,
yeah.
it's scattered. But your work is extremely important, and also is extremely important because by doing a decay study and having more well-calibrated constraints, I think you will be able to really pin down the actual past evolution of Neptune.
Yeah.
You have to realize that there is a huge portfolio of possibilities in these scattering models,
Yeah.
which can change really a lot from one simulation to the other simulation.
Yeah.
And so what actually Neptune did in reality is so far unconstrained. And so what your work and the new observations can really
Yeah.
help in constraining what actually happened.
Yeah, well, and I think another important thing to know is that the inclination distribution is still a problem. I don't think any of the models do a very good job with the inclination distribution. So I think that's one of the really interesting problems. If we can start to constrain the initial conditions, maybe we can actually figure out. It's really hard, it turns out, to pump things up to 30 degrees inclination. We need to figure out, did that mean Neptune was inclined at some point in the past, which I think is one of the more promising explanations, which that probably requires some sort of resonance and or planet-planet scattering to pump the inclination. But the inclinations are very problematic, and I totally glossed over that. But we don't know yet what happened to those. But I agree, there's a lot of evidence pointing to smooth migration not having occurred, but this would be the final definitive it didn't happen if we can measure the resonant distributions.
Okay, so let's thank the speaker again.